time with the online speaker. Our kind guest has been or is Cole Comfort from the University of Lorraine, and he prepared a talk for us about graphical calculi of phase-space representations in quantum mechanics. So thanks, Cole, for coming again, and the floor is yours.
Thanks for the introduction and for being invited to talk. Okay, so this talk is based on joint work with my co-authors Robert and Titouan, and we put two papers on the archive relatively recently, including the second one, which we put on came on the archive this Monday. If you want to check those out. Also, I have the slides are on my website. If you Google me, if you want to follow along. Okay, I'm not exactly sure about the background of everyone here, so I've made lots of slides, and depending on what reaction I get, I can go through some parts slower or faster, or maybe not cover parts that people find uninteresting. So please interrupt me at any time if you want. I'll be very happy to answer questions. Okay, so the general outline of this talk is, first I'm going to talk about string diagrams and graphical calculi. And then I'm going to talk about how you can do like linear algebra and affine algebra using only pictures, using a formal equational theory. Then I'm going to give a brief introduction to quantum mechanics, followed by talking about like symplectic linear algebra and Lagrangian relations. And then I'm going to talk about how this can be used to give descriptions of quantum circuits in finite and infinite dimensions. So this first slide is really important for my talk because most mathematics is done, algebraically with equations between like letters and symbols. But the whole point of my talk is going to be trying to reformulate things using only pictures. And particularly, I'm going to be using the structure of compact closed categories. I don't know how many people are familiar with this, but the basic idea is that you have the composition denoted by pacing things one after the other. And then your monoidal product, your tensor product, is given by putting them side by side. The symmetry allows you to cross wires over and you can slide things around. And then the compact closed bit means that you have duals, so you can bend wires. And the kind of general aesthetic of my research, the research of my co-authors, is how can we take things that are already known in computer science and in physics, and then reformulate them only using pictures in a completely formal, rigorous way. So the first thing that we're going to do is tackle how do you talk about linear algebra, and more specifically affine algebra using only pictures. So first I'll give the semantics. So you have this category of affine relations. The objects are the natural numbers, and the maps are not matrices, but they're subspaces, affine subspaces between the direct sum of a vector space with the input dimension, the number which is in the domain, and output dimension, the number which is in the codomain. And the composition, this is also really important conceptually, is you take the relational composition of the underlying subspaces. So you look at all of the points in both the subspaces, and you get a new subspace which contains all of the things in the intersection of both of the original subspaces. And this category has the structure which I described in the previous slide, namely it's symmetric. You can permute the elements to get the symmetry, and it's also compact closed. So you can relate the point to two copies of the vector and take the converse of that, and that gives you how you can bend wires. And in the literature already, there is generators and relations in terms of string diagrams for this category. So the basic idea is you have this gray spider which can have many legs on the input and n many legs on the output. And what this does is it just compares all of the elements of the n-dimensional vectors and requires that they're the same. So this is like a Dirac delta. And then what this white colored spider with this label A does is it sums both of the sides and asks that they're equal to A. So this is your affine behavior because A here is a constant. And then you have this other generator which multiplies. My claim is if you have all of these three kind of classes of generators, you can generate all of the affine subspaces. And there's this paper by Bunke, Sobocinski, Zanazzi, and Pirolu, where they impose an equational theory on these generators. And the idea is that this is complete, so that you can, instead of working with affine subspaces semantically and concretely, you can just do everything using these pictures. So when two of these undirected graphs touch together, they fuse into, so that they have more legs. And then similarly for this white one, and then the affine part fuses as well. And then you have like standard like algebra structure and convolution and all these things. So this is just kind of the starting, the language I'm going to be using throughout the rest of this talk to build more and more interesting things, ending with infinite dimensional Gaussian quantum mechanics and equational theory. And what I'll do in practice is not work with this equational theory itself, but take the stratification, which means that I'm going to be adding new objects, so that for every number of like wires that can be tensored together, I'm going to draw like a thick wire with indicating the number of wires that are like kind of sheathed up inside of there. And then I have also these generators which split and gather these wires to do kind of the combinatorics. And technically these are the representatives of the laxators for the monoidal functor. But the point of this notation is that whereas before I have everything, all of the generators only involve one wire, here I can kind of bundle them up and I can define these Dirac deltas, but now on systems of k plus 1 wires, and also these kind of affine spiders, where now instead of adding by a scalar, you add by a vector. And this allows you to define block matrices using pictures, because if you have this matrix A, B, C, D, you split the inputs up, copy them, multiply them by the constituent matrices, and then sum them back together. And then that's like the kind of inductive definition of a matrix using these pictures. So this is all just trying to build up from basic linear algebra using pictures, so that I can get to the more interesting stuff. So there's a normal form for affine subspaces. So you can either ask that an affine subspace is the kernel of an affine matrix or the image of an affine matrix. So using this notation, we can succinctly represent this by saying you have this affine matrix where the linear part is the matrix T, and the affine shift is this vector V. And then in terms of the pictures, this is the subspace that represents the image, because you're asking all of the vectors, if you multiply them by, or the kernel, all the vectors, if you multiply them by T, and then you add V, that is equal to 0, which is the definition of the kernel. And similarly for the image, you're here introducing, you're saying, give me any vector in this of this dimension, multiply it by the matrix V, and then add, or T, and then add V, and that's image. So this is like establishing the basic things that everyone knows about in linear algebra, but using pictures. Okay, so I'm not sure what the knowledge of quantum computing is, but this is a quantum-based seminar, so please interject if I'm saying something that no one knows about or that everyone already knows about. So in quantum computing, usually you fix some local dimension D, which is a natural number, and then the state space for n qubits, which is like the space of computation, is the Hilbert space spanned by d to the n basis elements, which I denote by j with this ket notation. So that like classically, if you have a particle, then it can have d possible positions. But in the quantum case, we're going to take normalized vectors in this space. So instead of asking that it only takes one, that like the particle only takes one value, we're going to ask that it's a normalized vector in this Hilbert space. So that's like the notion of a pure quantum state. And then the purely quantum evolution is given by unitary operators. So these are the things precisely that preserve the normalization. So like a quantum computer that is not connected to the exterior world. It's just a purely quantum thing. You have these pure states and unitary evolution, and that's how it evolves over time. But for my purposes, being a category theorist, this is a way too restrictive of a setting to work in. And instead, what I'm going to do, at least initially, is work in qubit Hilbert spaces. So this is the full subcategory of Hilbert spaces, or equivalently of matrices, but now where the objects are generated by like these qubit Hilbert spaces that I gave before. So like these the span of these vectors. And here, this is again a compact closed category, given where the monoidal structure is given by the tensor product, and the compact structure is given by these cups and caps. So you take the one object basis element, the field, or the one dimensional basis element, which is 1, and then you map this to the outer product of all of the basis vectors. That's like the cup, and then the cap is you take the outer product of 2 different basis elements and you send them to the Dirac delta. And this is a dagger category, which means you can also flip the morphisms around using the Hermitian adjoint, which is, in terms of matrices, this is the complex conjugation transpose. So all of this means that you can, instead of representing a linear operator in this category by using this kind of maps to notation, what we're going to do is refer to linear operators using a sum over the exterior product of the basis elements of the domain and the basis elements of the dual space of the codomain, right? So any linear operator is like described by this kind of a matrix using this notation. Okay. So in quantum mechanics, oftentimes we don't think of pure states themselves as being physical. What we'll do is we'll take the rank 1 projector onto the Hilbert space. So this is the exterior product of the quantum state with itself. So recall that I required that this phi, to be a quantum state, all it has to be is to be normalized. But really what I'm going to think of it as is an endomorphism on the Hilbert space given by the outer product with itself. Because the reason why this is done is because then you can talk about quantum measurement. And in quantum mechanics, a measurement is usually done with respect to an orthonormal basis. And so if you have your pure quantum state phi, and then you have this orthonormal basis psi indexed by j, then the Born rule states that measuring the state phi with respect to the basis yields an outcome indexed by j with a probability given by this inner product absolute value squared. So that's just like how measurement is defined. But again, to me, this is like way too concrete and not categorical enough to be well behaved from a mathematical point of view. Think of it this way. So what I'm going to do first of all is think of measurement not as some external thing that a human can do, but rather in terms of an operator on Hilbert spaces. So what it does is it takes an element of the internal Hom from the Hilbert space to itself and produces a new element. So if you take your pure state phi here, which I've represented by taking the outer product with itself, then it maps this to the sum where you conjugate by the projectors onto all the basis elements on both sides. And then by just moving things around, you get that. Now you have a sum of all of the different basis elements where the coefficient is given by the probability of measuring them. And these probabilistic measures of pure quantum states are called mixed states. So to do a computation, you need to do a measurement. So really, this is what states in a quantum computer are actually modeled by, because you can't do a computation without the measurement. And there's this general construction due to Selinger, where if you start off with a dagger compact closed category, so where you can bend the wires around and flip them around with the dagger, obeying certain coherence laws, then you get a new category, which is called CPM of the original category. And the idea is it has the same objects, but now maps are given by, you take your map in your original category, and then you bend one of the wires around, and then you compose it with the conjugate. And this is a dagger compact closed category. And the whole purpose of doing this is because this kind of way that I've stated measurement now becomes a morphism in this category. So here, now the physical things are called trace preserving. It's like when you have this cap in the middle, it's trace preserving if you take the cap and you apply it to all of the outputs, and then the cap can kind of pass through and become natural, and then you get a cap on the inputs. And the trace preserving states are precisely the mixed quantum states, and the trace preserving maps are like the maps which are interpreted as being physically possible. So now if you work in this new category which I've constructed, which is this CPM, density matrices over qubit Hilbert spaces, you have like now a more appropriate semantics for quantum computing. And that is, you take mixed quantum states as the possible states of your system, which are modeled by these trace preserving states in CPM. And the quantum evolution is the trace preserving maps. Yeah, the thing is, this is a very, very large category, and it's very complicated. And the point of my talk is I want to restrict my semantics to a smaller fragment of quantum mechanics, so that it can be faithfully represented within this kind of way of thinking of things, but where it has more kind of classical behavior that's more reminiscent of classical mechanics. And to do that, I need to change my my way of thinking. Instead of state spaces to phase spaces. So in the previous kind of very brief introduction to quantum mechanics, I described that the state of space, the state space of a quantum system is, you have this Hilbert space, d-dimensional Hilbert space, tensored n times itself, and these are all of the different possible positions which your particles can take, and of course also the mixtures of these things. But there's another way you can think of things, and it's in terms of the phase space. And what this means is, instead of thinking of a quantum state as being a linear combination of, or a mixture of a linear combination of positions, you think of it as having a position and momentum, and maybe certain relations between those two things. And this is broadly how classical mechanics is done, or at least Hamiltonian mechanics. That you have a particle, like imagine a bowling ball or whatever, just a classical particle, and it's described by its position, its momentum, and if you now play out the evolution of this particle, it will bounce, hit something, the momentum will change, the position changing is velocity, and so on. So the question is how do you how can you restrict quantum theory so that it can be described faithfully and completely rigorously using these terms? And also, moreover, how can you do it only using pictures? So that's the motivation of our research, really. How do you take classical mechanics, extract some fragment of quantum mechanics, and avoid having to ever use algebra if you ever don't want to. You can always use pictures. Okay, so the mathematical foundations for phase space is symplectic algebra or symplectic geometry, but I'm not going to be concerned with nonlinear stuff, or at least non-affine stuff, because it's too complicated to give pictures for. So I'm going to just give a brief review of symplectic, linear, and affine algebra. So a symplectic form is a bilinear alternating non-degenerate map on a vector space. And a symplectomorphism is a linear isomorphism that preserves the symplectic form. And every symplectic form is symplectomorphic to this one, which I denote by omega sub n. And you take your two vectors, and then you kind of twist them, take the inner product on both sides, and subtract them. So what does this mean conceptually? The fact that every symplectic form is equivalent to this one of this form means that you can always split your vector spaces into two, and you can think of the first n parts of your vector space as being the different possible positions, and then the last n as being the different possible momentums, so that your particle now is a vector of n positions and n momentums. So it's n particles given by n positions, n momentums, and then the kind of invertible Hamiltonian evolution of this particle is given by something that preserves this form, which captures like the commutation relations of in mechanics. Okay. And I'll also need to talk about how symplectic structure interacts with like linear and affine subspaces. So if you have an affine subspace of a symplectic vector space, you can define its symplectic complement. And what this does is you take the linear part of the affine subspace, and then you look at all the vectors that commute with the subspace with respect to this form. So this is kind of like a symplectic version of like the orthogonal complement of a subspace, except you replace the inner product here with this symplectic form omega. And there's three really important kinds of subspaces. An isotropic subspace is an affine subspace that is contained within its own symplectic complement. A coisotropic subspace is the other direction. And then Lagrangian subspace is it's both isotropic and coisotropic, so that the subspace is self-dual with respect to this operation of taking the symplectic complement. And kind of one way to think of what this means, first I'll focus on the Lagrangian subspaces, is you have like you have a physical you have a classical mechanical system of particles with positions and momentums, but you want the particles positions and momentums to be like the least possibly constrained the least possibly constrained like kind of a description of a system in terms of the position of momentum. So instead of having definite knowledge of the positions of momentums, you're kind of having this ensemble of states which you know that the particles can possibly be in, and that's described by the state space is described by a Lagrangian subspace in classical mechanics. And just like affine relations form affine subspaces form a category of affine relations, these Lagrangian subspaces, affine Lagrangian subspaces, also form a category, and it's pretty much the same idea as affine relations, except now the morphisms, you have to be a bit careful, and you have to say you have domain n and codomain m, then the morphism is a subspace of k to the 2n plus k to the 2m, except now with respect to this new symplectic form which I'm defining, omega sub nm. And what this does is it takes the inputs and output vectors, and it takes the symplectic form on the output and then subtracts that by the one on the input. And if you define this category this way, then you can define the composition in terms of the relational composition, just as in affine relations. And the complex structure is a bit different because you have to insert this negative sign. And there's also a dagger given by you negate the momentum gradient of the subspace, but not the position. And in our first paper, me and my co-authors, what we do is we give a presentation for this category, so you can think of it only in terms of pictures. So what we do is we pretty much generalize the generators of the affine relations, except now we decorate these graphs with two different numbers in our field. And the first one, so if you have this gray spider, then the first number denotes the affine shift in the momentum, and then the second scalar represents like the slope in the momentum, and dually the affine shift in the white spider it's the affine shift in the position, and then the B for this white spider is the slope in the position. So like these two spiders are kind of doing dual things to each other, and when the position spider acts on the position basis, it acts as the direct delta on the momentum basis, and vice versa. So just to give you some kind of conceptual idea, and we have given generators in our paper. So it's the same kind of idea. You have these like undirected graphs, these spiders, and when they connect together, then both of the components, the affine shift and the slope, sum together. So you have this in both both in the position and the momentum. And also you have this kind of these derived generators, which you can define using these two classes of labeled graphs. So particularly you have this A box, and when you take A to be 1, this corresponds to the symplectic Fourier transform. And when you take A to be -1, this is the inverse symplectic Fourier transform. And then what you can also do is if you compose an A box with the inverse symplectic Fourier transform, this gives you the scalar multiplication of A, but in a doubled sense. So what this does is this multiplies the position by A, and then it divides the momentum by A, which respects this duality that I was kind of trying to sketch on the previous slide. Yeah, and then of course, if the spiders are labeled by the identity of the group, which in this case is 0, 0, then just so we don't have too much clutter going on, we will just omit the label. Okay. And recall how when I discussed the presentation of affine relations, what I did was I gave like these inductive definitions for how to define block matrices, so that we can talk about kernels and images of subspaces in a succinct way. But here, there's a lot more structure. In particular, because you have these two phases, if you do the same kind of thing and you define these like spiders, but on higher dimensional systems, then what you get is this inductive definition. And essentially the idea is if you have K wires bundled up together, and then you have a spider where the wires correspond to these K wires all inside of it, then the things are now labeled by a vector of dimension K, and then also a symmetric matrix, a K by K symmetric matrix, which is kind of like, you can think of like the adjacency matrix of a graph. So here I've given an example of such a thing. If you set K to be 3, and you have 0 outputs and 0 inputs and 1 output, so and you label it by this vector X in this symmetric matrix big X, then you can kind of unroll this inductive definition, and you find that the matrix, the elements of the symmetric matrix give you the edges, and the second element of the label of the vertices in this graph, and then the affine part of the vertices is given by this vector. So here we're kind of mixing the like matrices and the string diagrams, because in order to prove that this language is complete, this is like this kind of level of generality where you work both with pictures and with matrices. It makes the proof much simpler. Okay, so this is the normal form that we use, for example. So this is one of the utilities, one example of the utility of the seemingly complicated construction we've given, is that every affine Lagrangian subspace you can uniquely represent in this way. So you have this affine shift. Well, basically the idea of the kind of shape of this graph is you have, as before, you have this thing expands into a graph, but the first m edges, or the first m vertices of the graph, are like not connected to any outputs. So we're just plugging in, like kind of we're plugging in a hole in the outputs of the first m parts of the graph, and the second n are like these external vertices which can interact with the rest of the environment. Yeah, I don't want to talk too much about like what the specifics of what this means, this normal form, but just to say that this notation, you can represent the normal form in very small picture. Okay, so now that I've given this language, this is kind of like the language with which we can talk about these quantized fragments of these classically quantizable fragments of quantum mechanics. So this is like our kind of graphical language for mechanics, and we know that these rules are complete. Okay, so the first thing I want to talk about is finite dimensional quantum circuits and the things we can represent this way. So if you fix P to be an odd prime number, and odd is important for annoying technical reasons, because at some point you have to divide by 2, then this prop which we've axiomatized of these affine Lagrangian relations over Fp is a projective representation of what's called Q-pit stabilizer quantum circuits. So like the dimension, the state space or the phase space is given by P. So it's like Q-dit, but for primes. And the basic idea is that every affine Lagrangian subspace, or every affine Lagrangian relation, you curry into a state, and then you map this affine Lagrangian subspace to a stabilizer state, which is this rank 1 projector given by, you take this big sum and tensor product, and the idea is that the momentum changes this complex phase here, and then the position shifts the vector space structure in like the state space representation. So this is a bit technical, but just to show that somehow the position and momentum are showing up in this formula. And if you do all of the work and stuff, you can show that if you uncurry these states, if it's an isomorph, if the original thing was an isomorphism in affine Lagrangian relations, it was an affine symplectomorphism, then this is the same as a Clifford operator, and so on. And you get, in fact, that up to scalars, this is a subcategory of Hilbert spaces. So this is like a fragment of quantum mechanics in some sense, but only of pure quantum mechanics, which I discussed earlier. So there's no, at this point, there's no interaction with a classical observer measuring anything. This is the purely isolated quantum fragment of finite dimensional quantum mechanics that can be described purely in terms of the configurations of the position and momentum and their evolution in terms of how the position and momentum changes. So just as I gave the kind of general pure state quantum mechanics schema for how things can be prepared and evolve over time, in this fragment, you can prepare stabilizer states, which we represent by affine Lagrangian subspaces over this finite field. And then what would normally be the Clifford quantum evolution, we represent this by taking the graph of a symplectomorphism, and then of course everything can be composed by relational composition. But like I said, this is only the pure stuff. So what about mixed things? Right? Because I recall I give this general categorical construction of Selinger of density matrices given a compact closed category. So the natural question to ask is, what if you take the CPM of affine Lagrange relations, or what if you take density matrices of stabilizer states? And in fact, when you do this, this is equivalent to so adding quantum discarding, adding the trace, or adding measurement. This is the same as shifting from affine Lagrangian relations, where the morphisms are Lagrangian subspaces, and relaxing this so that they're only affine coisotropic relations. So if I go back to the definition here, right, a subspace is Lagrangian if it's equal to its own complement, and coisotropic only if it contains the complements. So this is a strict relaxation of the original requirement. Oops. Yeah, and it turns out even over any field, what you can do is you take CPM, show it's equal to affine coisotropic relations, and this is the same as adding the discard relation. So it takes the position of momentum and it relates this to the point, so that you can kind of just throw away any position momentum. And if you consider this kind of discard relation as a generator itself, then on top of the equational theory of affine Lagrangian relations, we just have to impose the equations that it discards all of the isometries, which is given graphically by these equations for any A and B in your field. So in this case, over FP, all of these numbers will be integer modulo P. And now you have a graphical language for stabilizer quantum mechanics with discarding. And this is somewhat useful because this isn't just some random fragment that I've chosen for no reason. It's well motivated, and particularly because, in quantum error correction, the fact that you have this phase space representation is very important because it makes things tractable, and this is the primary kind of tool which people use to try to correct for errors. So this is working with stabilizers is a very, very popular thing to do. Yeah, so if hopefully the things I've talked about so far, there's some level of comprehension. Yeah, like I said, I don't know the exact backgrounds of everyone, but now basically the idea is we take this stuff we've done in finite dimensions and we ask, is there any way which you can abstract this away to continuous variables? This is a notoriously difficult problem among people who are trying to give equational theories for quantum circuits, because infinite dimensional Hilbert spaces is a lot less well-behaved than finite dimensional Hilbert spaces. So particularly what I mean is you work with a category of Hilbert spaces. So now the objects are in a subcategory of what's it called? Separable Hilbert spaces, where the objects are now these Hilbert spaces of square integrable functions on Rn. So the idea is instead of the Hilbert space being the span of finitely many vectors of a basis, here I'm saying the Hilbert space is a space itself of functions, such that if you integrate, you take the Lebesgue integral over Rn of the function the absolute value squared, then I'm asking this is finite, and this forms a Hilbert space. But the problem is, for example, there's no duals in this Hilbert space. So this is one of the difficulties of axiomatizing stuff, because all of these spiders and the graphs and stuff that we've been using, this all heavily relies on having duals and compact closure. So like all of the existing languages in the literature, they kind of leave this paradigm of describing things in terms of these interacting spiders, and they have to be more rigid in how they construct circuits. So our motivation is like, can we get around this by, instead of working in these Hilbert spaces, working in this kind of phase space representation by changing, for example, the field from a finite field to the real numbers, because the finite field is only discretely many possible positions and momentums of a particle, but at least intuitively, if you change to the real numbers, then now your particle is the position momentum is described by a continuum of different possibilities. But indeed, this intuition is kind of correct, but not completely, because if you look at the affine symplectomorphisms over the real numbers, at least in finite dimensions, then there's this group is projectively represented by what's called the Gaussian unitaries between these Q modes. But the problem is the states. The states don't make any sense, because if you think of what affine Lagrangian subspace, say of R2 is, then this is just given by a line in the real affine plane, and that's completely discontinuous, which means that it can't be correspond in any way to a morphism between Hilbert spaces, because a line is like, I've rendered this kind of visualization. If you just have a affine Lagrangian subspace over the real numbers, say in the case of just one particle, then the state is described by this like infinitely thin line, where the position is like, and the momentum are definitely at this point, and then if you move just epsilon far away, then it's zero. And yeah, this is completely not bounded or not continuous. So we have to figure out a way to get around this. And the way that this is done by physicists usually is you take convolution with the Gaussian distribution. So what I've drawn on the right is, you can kind of think, if you look at it, it's kind of in the same shape, but clearly it's not this. It's not the same thing. But now you actually have a Gaussian distribution instead of just this weird Dirac delta thing. Okay, so now this is a bit technical, and I'm gonna just put all of the equations on the slides, but you know, you don't have to like read everything and understand the technical details. But this slide here is, I'm just introducing what is a Gaussian distribution itself for people that have forgot or that are not familiar. And what I'll need is the kind of n-variate generalization of Gaussian distribution. So normally, you know, like a single variable Gaussian distribution is described by a mean, which is like a point on the real line, and then a covariance, which is just a number, a positive number, or non-negative number. But here, what I'm going to need is I'm going to need a vector for the n-variate version, and also a positive semi-definite matrix. You know, so if you are thinking back of when the previous slide, when I labeled these string diagrams with symmetric matrices, this is kind of hinting towards what I'm going to try to do on the next slides. And in particular, when this matrix signal called the covariance matrix, when it is positive definite, not just semi-definite, then it has a density function, which is, you know, this is one example I've drawn here. So if the matrix is not positive definite, but only positive semi-definite, you can't draw this picture. But this is just to help you kind of intuit what is going on, because you don't always have that it's strictly positive. Okay, so the idea is you take affine Lagrangian relations over a field, and somehow you need to find a way to add Gaussian noise. And then my promise to you is that this will give you the kind of right setting to talk about infinite dimensional phase space representable fragments of quantum theory. Okay, so that was Gaussian distributions and probability theory, but now I'm going back to quantum theory in infinite dimensions. In the Gaussian state on this infinite dimensional Hilbert space of square integrable functions on R to the n is a quantum state of this form. So it takes, you know, some vector x in Rn, and it produces you know, this thing on the right hand side. We call this is determined by some arbitrary some phase alpha, which we can kind of forget about because it doesn't. We're only going to be able to succeed to find a projective representation anyways, so we don't care about non-zero scalars. And then there's also these two variables, s and t, and together we'll call that the displacement. And then this phi, which comes up both here and there, which is this symmetric matrix whose image is strictly positive definite. We're going to call that the displacement matrix. And in the literature, this is like kind of the continuous variable generalization of a stabilizer state, things of this form. But of course, what we're going to try to do is to forget about Hilbert spaces and see if we can just work within the phase space semantics. Yeah, and a really important Gaussian state is called the vacuum. So there's no displacement, and the phase matrix is just given by I. So this is like kind of the state of Gaussian noise in your quantum system. Okay, so the Wigner transform is this transform which is known. So it has this form, so it takes a quantum state on L2 of R to the n and produces a quantum state on L2 of R to the 2n, such that it's real. So it loses all of these functions are all real and not complex. And this is the formula for it. And you can do this any quantum state, but if you do it to a Gaussian quantum state, this is like the really crucial part. It's that if you do it to a Gaussian quantum state, then you can describe fully and faithfully up to scalars the Gaussian quantum state in terms of a Gaussian distribution. And the Gaussian distribution has a covariance matrix given by this thing here. So you take the image of the you take the imaginary part of the matrix and the real part of the matrix, and you assemble them in this way. And this is a Gaussian distribution, and also the what I called the displacement back here. You just take this vector and you just chunk it together, so it's a vector in R to the 2n, and this is like the mean of your Gaussian distribution. So I've doubled the dimension. I've removed all the complex stuff. So now I have an honest Gaussian distribution on R to the 2n, which will be our phase space. Again, you can also go in the other direction. If you have a Gaussian distribution satisfying these conditions, this precisely gets you back to a Gaussian state where you take the matrix elements, and you do this thing, and you multiply the inverse of I with C, and you sum that together. So the way that this works is kind of mysterious to me. It's just it's very beautiful, but to me it's almost like magic that this works. Okay. So this is now approaching the end of the talk and the crux of the talk. If you take affine Lagrangian relations, but you ask that they're not over the reals, but that they're over the complex numbers, and you impose a further condition that the subspaces are affine Lagrangian, you impose furthermore that it's positive. So if you take the symplectic form and you multiply it by A and evaluate it on all of the elements of your basis with themselves, that this is greater than 0 for all of the elements of the subspace, and where you also ask that the affine shift is a real number and not just complex, then I'm calling this a complex or a positive affine Lagrangian relation, and this forms a subcategory. So this looks like a bunch of like maybe unmotivated, weird inequation, but it turns out that the Wigner representation of the Gaussian state is precisely a positive affine Lagrangian relation, and you can represent. All you have to do is you start off with the presentation of affine Lagrangian relations over the reals. What you do is you add shearing or the slope by I only, and by no other complex numbers, and this generates the entire complex or the entire positive complex Lagrangian relations. And this is kind of the idea: is you have your Dirac delta here, which is given by this a line, and the line is represented by this subspace of C to the 2, a real subspace of C to the 2, and then you take your vacuum state, your Gaussian state, given by 0I. You squeeze it by the square root of E, and then you sum that to this. And this is the same as performing Gaussian convolution by this matrix. So as it convolutes, say, the position by epsilon, it convolutes the momentum by the inverse of epsilon. So the volume is always being preserved. And instead of thinking of things in terms of complex affine Lagrangian relations, we can think of it in terms of adding this generator I to the real case modulo equations, so that we don't have to rely on the equational theory of complex numbers at all. And just like when we added discarding to stabilizer circuits by going to coisotropic relations and discard the isometries, here what we're doing is we co-discard the symplectic rotations and the effects. So these equations look like this. You have your rotation matrix here, and you plug in the vacuum state, and this produces the vacuum state. And then this seemingly mysterious composite here is like actually the internal rotation of the affine plane. So you can imagine rotating inside a single wire. There's c squared, and you're rotating this around the real plane. And you're asking that if you precompose this with the vacuum, you get the vacuum. And this is enough equations to reason about all of Gaussian quantum mechanics. And kind of some intuition for how this works is if you take the vacuum Gaussian state, this is represented by this positive complex affine Lagrangian subspace, just given by convolution at the origin by the standard normal distribution. And this is the only distribution which is going to be invariant under rotation. Because if it kind of trails off more in one direction than the other and the covariance is different, if you rotate it, it's not going to, the symmetry is not conserved. So this stuff that we wrote about why you have to discard the rotations is because if you rotate this figure I've drawn, it's always the same. And this is in some sense like the universal property of what it means to be the normal Gaussian state. Of course, in higher dimensions, I can't draw a picture, but you can kind of try to think that it might be reasonable at least. But if someone has any way to think of how to visualize this, then I would be really happy. And our motivations are kind of coming from computer science. So we want to ask, can you do algorithms and quantum protocols using this language? So what I've done is I've reproduced this continuous variable Gaussian quantum teleportation algorithm by these two authors. And now Alice and Bob, they share a Bell state, which in finite dimensions, you draw like a cap. But here in our phase space semantics, we can represent that, but it has no physical interpretation. So what we do is we take a Bell state and we perform convolution by some Gaussian noise. So Alice, they share this Bell state here, which I'm like circling. And then Alice performs a Bell measurement, Bell homodyne measurement, and receives two real numbers as her measurement outcomes, A and B. She sends this classical information to Bob, who performs the phase correction in the position and the momentum. Then we simplify the circuit, and what we see is that the way in which we convolved the Gaussian state to make it continuous affects the error on the channel after teleportation, which is the kind of the main result of the original paper, which did this all using Hilbert spaces and not using the phase space semantics. But in fact, our semantics is sufficient to express this, and I would argue is kind of the correct thing, because the usual way of talking about Schwartz distributions, you can't compose them relationally. And in fact, also in our semantics, we have the infinitely squeezed limit. When you have a perfect Bell state, which doesn't physically exist, we can just, at this penultimate step, we can just set epsilon equal to 0, and then we'll find that they've transmitted a perfect channel. Okay, so this is the end of my talk. I'm going to just talk about the future directions that I want to work in, and if anyone has any other ideas. So the general thing that I've done is we've taken these different my co-authors and I have taken these different Grassmannians, which represent some kind of symmetries in quantum mechanics, and we've composed them relationally and got categories. So in particular, we've done this with affine subspaces, affine Lagrangian subspaces, affine coisotropic subspaces, and these positive affine Lagrangian relations. And at each step, this has given us different fragments of quantum theory, which we can interpret using our equational theories, which we've come up with. So my question is, what other Grassmannians are useful in quantum mechanics, and can we do the same things? For example, if we drop the symplectic structure and just work with the inner product, then we have the orthogonal Grassmannian, which is like the kind of fermionic version of the bosonic picture represented in this talk. What do we get there? Can we do the same thing? Can we get some string diagrams for boson, the phase space representation of fermionic quantum mechanics? Similarly, if we work over the field of formal Lorentz series, say over the real of the complex numbers or finite fields, three examples that we've discussed here. Can we talk about generating functions if we swap the symplectic form so that we invert the second argument, the polynomial in the second argument? It seems to me that this is kind of the way that people talk about dynamics and generating functions in mechanics. So I think these are two natural ways which we can try to expand the work and try to axiomatize more of quantum mechanics using just pictures. And that's the end of my talk, and I've included some references. So.
Okay, thank you very much for nice talk and pictorial approach. And thank you very much. So it's time for questions, remarks.
Hi, I'm Cole. I'm Daniel. Yeah. Well, it's for me a bit kind of unusual use from the point of view of Lagrangians. Normally, I would think if you talk about Lagrangian subspaces in symplectic spaces or in the context of geometric quantization, polarization, and maybe coherent state quantization and these kind of things, even in relation with Grassmannians or homogeneous entities. So is there any kind of relation between these things, or should I think about them like something very different? Or
between which things? I didn't hear the... You're too far away from the microphone. I didn't hear what are the two things?
Oh, I think that I'm just used to hear this word in the context of geometric quantization, let's say.
Oh, I see. Yeah. Oh, yes, I can answer your question. Yeah, so this is essentially what we've done, but in geometric quantization, you start off with the symplectic manifold, and then to take to construct the Weinstein category, you have the morphisms being Lagrangian submanifolds.
Exactly.
But yeah, what we've done here, because manifolds, they don't admit a nice graphical calculus, so we've restricted everything to the largest possible nonlinear thing which we can capture, and that's the affine subspaces. So we've done all of the same stuff, but we've made the restriction that everything is affine instead of manifolds. Yeah. And by working at this level of specificity and this lack of generality, then you can concretely give these presentations for things which people are doing in quantum computing.
Thank you. Yeah.
And there's a question in the chat. Let me read it. Yeah. Do I understand correctly that it describes some interesting subset of quantum mechanical states of a particle in Rn? Which subset of these? Can I see the Schrödinger equation or evolution in your graphical calculus?
So your question is almost your understanding is almost correct. It's not like the phase space isn't okay. If the state space is L2 of R to the n, then the phase space is particular affine subspaces of complex numbers to 2 to the n. So yeah, the complex structures. Yeah. So you can represent you can only represent the states which have kind of probabilistic representations. So I don't know like when the Wigner function is positive, yes, positive. That's the only states you can represent. The problem with the Schrodinger equation and evolution is that we haven't figured that out yet. But this is one of the things I want to tackle next, which is well, I gave this header, twisted affine coisotropic Grassmannian, which I don't know if there's a better name, so it's very hard for me to search for it. But the idea is by encoding, I want to encode the evolution of the quantum state in terms of kind of like a Taylor series, so that I can talk about differentiation by like a discrete value in terms of multiplying by the polynomial s. So that's what I want to figure out in the future. If anyone has any tips or something, but at the moment that's not.
Yes. The additional question: whether you do expect that these states are preserved under time evolution?
Which states? Oh yeah, they're only preserved if you do like the Gaussian unitaries. So if you if you just apply an arbitrary unitary or a measurement that is in the wrong basis, then immediately I think in fact if you do anything that is not a Gaussian unitary in any measurement that is like not the one I've described, then you immediately leave this fragment of quantum mechanics, and then you're lost, and then you can't. This is helpless.
Okay. Any other question? I would maybe have one. There is a way how you, via this graphical representation, can represent also nonlinear relation when you have some nonlinear symmetry imposed. Is there a way of treating this?
The closest we can figure out at the moment is affine, which is pretty much linear, because yeah, but I think that's something that some people are trying to work on, but significantly more difficult, because then that's in the realm of doing algebraic geometry using pictures, which I think most people would agree is a lot harder than linear algebra.
Yeah, I see.
But that would be interesting to if that does work out eventually.
Okay, and maybe one other not very related question. Firstly, you spoke about a finite dimensional case, and then switched to infinite dimensional, but entirely non-countable. So how about intermediate steps, like when you have countably many dimensions in your Hilbert spaces?
Yeah, I think because this condition of that we've given here, for example, really we've done it in a very evil way, because yeah, we wanted to do things as concretely as possible in the paper so that it's understandable to computer scientists. But if we were to do things properly in the most general way possible, then you can define this condition with respect to any arbitrary complex structure. So, for example, you could work over the field of rationals where you adjoin the square root of -1, and I think that would be countable. I don't know, but you could take L2 of you could take the state space to be L2 of some rational vector space, and then the phase space would be the complex rational subspace or complex rational vector spaces. So that's pretty cool, but I don't know.
I see. Okay. Any other question? possibly from online audience. Seems not to be the case, so thank the speaker again. Virtual applause is appearing.
Thank you.